Hello, everyone. Thank you for joining us for another live webinar session hosted by EE Tech and All About Circuits. My name is Dale Wilson, and I'll be your moderator. Today's session is brought to you by MacroFab and is titled Enhancing Operational Safety, Cyber Resilient Approaches for Physically Secure PCB Designs. Let me tell you about our presenters. Since 2018, Misha Govshteyn has been at the forefront of MacroFab as its CEO, driving innovations that are shaping the future of the $480 billion electronics manufacturing industry. With its technology manufacturing platform and expansive factory network, MacroFab is setting new benchmarks for excellence and innovation. Our second presenter is Brenden Duncombe. He is the Director of Customer Engineering at MacroFab, where he leads cross-functional engineering teams through the entire lifecycle, from initial prototyping to full-scale manufacturing. During today's presentation, we will post several poll questions to gather insights and feedback from you, our audience. And following the presentation, we will have a live Q&A with Misha and Brenden. You can submit those questions at any time during the webinar using the chat box on the right-hand side of your screen. We will provide attendees with a downloadable copy of the presentation near the end of today's session. This will be available in the Resources tab, along with a few other helpful documents that you can access at any point during the presentation. So thank you so much for joining us. And with that, I'll hand it off to Misha to begin today's presentation. Welcome, Misha.
Thank you very much. Since we've already gone through introductions, we're gonna start by talking a little bit about the agenda for this meeting. As previously mentioned, I have a lot of experience in the cybersecurity field. Spent many years with threat research teams directly reporting to me. A lot of late nights deconstructing attacks. So we have Brenden, who is a lifetime design engineer and really a specialist in electronics that can cover a lot of specific ways that we can secure PCB designs. But my objective in this discussion was to really take a step back and really help people understand where these designs getting compromised could actually fit in the overall kill chain or the sequence of events that happens as environments are being compromised. That's a very complex chain of events that usually happens. And it's important to understand how and why attackers choose what they attack. A lot of times we look at what they're going after, and it's very difficult to tell why somebody would want to attack that asset until the final stages of the attack, until the final objectives are clear. It's oftentimes very difficult to tell why somebody's attacking something that looks trivial and unimportant. So we're going to go through fundamentals of what security for electronics environments means, go through some examples of cyber threats and attacks that I think are especially relevant to this domain. I'm going to spend a bit of time going through examples of how the highest profile attacks have been executed. They're going to be broader in scope than you might expect. Again, we're not strictly focused on what it takes to compromise electronics devices. We're talking about what it takes to accomplish cyber threat objectives, right? And I think the electronics and hardware are a stepstone in that journey as opposed to the endpoint, and in a lot of cases. And then I'm going to turn things over to Brenden to go through the specific steps that you may want to take as a electronics designer, as somebody who's actually responsible for design and functionality, but also security of that design, assuring that. And by the way, you should think of security as a quality condition. If you design the device to work a certain way, and it ends up being compromised by attackers in the future, I would treat that as in a very same way as a design flaw, because ultimately somebody broke out of the design intentions, and it may happen very late. It may happen years after your design has already seen the light of day, but ultimately I would still consider that to be a design failure. So I think security should be one of those things that we take into account as a design objective. So to very quickly go through the fundamentals of, and by the way, there is there should be a poll popping up in front of me. We would appreciate your questions, your answers along the way. There's about 3 of them. They're easy to answer, so you can just submit and move forward. Just to quickly cover the fundamentals of PCB design security overall. First of all, there's a lot of vulnerabilities that are really concentrated on low-cost devices and even hardware chipsets that may not be used in production. I'll give you an example of where that happens. So it's not necessarily a device. In some cases, it could be components, and it could be things that you're not actually even necessarily yourself responsible for. I'll give you an example where hard drives, for example, are the compromised medium and become an entry vector for an attacker, right? There's a very diverse spectrum of devices out there in the field at this point, and that's what makes the job of defenders much more difficult. Coming from the cybersecurity world, I will tell you that most of the topics that we're discussing on this webinar are a bit of a dark art to a lot of people. If you go to Black Hat, if you go to DEF CON conferences, especially at DEF CON, there's a lot of times sessions on how to break into hardware devices. But overall, in the mainstream, usually the people that are in the cybersecurity domain kind of fall into 2 categories. They're either software, they either have software background, or more likely they have DevOps or admin background. So in all honesty, I think they find electronics to be incomprehensible. And for that reason, in all of the work that I've done, and I've personally done SCADA assessments in environments where they're supposed to be air-gapped, in all of those walks where I was deeply involved into critical infrastructure security, I can't count any situations where I came across double E's or design engineers that should have been part of that process but were not. And so that's part of the broadening of the spectrum that we want to expose here. Having said that, I think you can certainly go crazy enumerating an infinite number of ways in which you can get compromised. So there's diminishing returns beyond a certain point. I would think that thinking broadly and really understanding the threat model and all the ways that your design can be compromised is extremely valuable, but eliminating every possible attack scenario, I don't think is valuable. And for that reason, and after the examples, I think it'll be obvious why I'm saying this. Ultimately, you have to know who you're protecting yourself from. And my conclusion after decades in the cybersecurity industry is that it's somewhere between very difficult to impossible to build a perfectly secure system that can withstand a really determined attacker. And I'm not talking about 300-pound hackers in Russia hacking in their underwear. I'm talking about nation states that have infinite resources, massive budgets, can get access on any equipment. The range of attacks they've executed has been incredible to me, and the more I learned about it, the more I realized that you should do a reasonable level of security design thinking. But ultimately, if somebody really wants to get through, they will, and you'll never be able to eliminate 100% of possible attack scenarios. And ultimately, it is an exercise in minimizing the attack surface, right? So I wanted to start this discussion with really the most recent attack that just hit the wires, and you don't have to read through that entire list. We're certainly happy to send you the presentation so you can understand how that attack was executed. I highlighted the things that are most relevant for this discussion. First of all, the reason I'm out of the industry, but this one really came on my radar because this is the holy grail of attacking somebody. And by the way, there's some discussion about who exactly is being attacked here. My understanding is that this is the NSA attacking either Kaspersky Labs people themselves or just iPhones being used in Russia. So these are nation states going at it with each other. But the holy grail is to execute an attack that doesn't require user action at all. So in this case, a malicious iMessage attachment that didn't need to be clicked on, did not need to be executed, was still enough to actually fully compromise an iPhone. Now, iPhones are obviously self-contained devices. They're not really typically operating in a, aside from iCloud, most of iPhone security is really, and these are, by the way, some of the most secure devices out there. We're talking about a single device that the wealthiest company in the universe has a lot of resources to ensure that it's secure. None of you will get anywhere near the level of budget or attention on your devices that you're building that Apple is spending, and yet it was still compromised, and it was done with a holy grail of all exploits where user action is not actually required. What's amazing about this exploit are two things. One is that we're used to multi-step attack kill chains, right? So when you look at every icon in that graphic, usually they look like 3 to 4, maybe 5 steps in a sequence, right? And this is the most important thing to understand about kill chains. They're never, look, we're long past the days where a single step could get a device compromised, right? Back in the days, people used to expose their SQL servers to the internet, and a single, symbol malformed SQL query could get you compromised an entire environment. Nobody does that anymore. There is no simple single step attacks out there. What's mind-blowing is that they're getting more and more complex. They're combining not just kind of the holy grail of all attacks where no user action is required. They're also using memory registers that aren't even published. I mean, what's amazing about this attack is that nobody truly understands how the attackers got their hands on this instruction set. It is hardware functionality that isn't published. It appears to not actually be used. What I thought was really interesting is that, look, I think this is an example where I actually do believe in security by obscurity, but at one point, maybe in the earlier versions of these designs, somebody was using these hardware features for testing purposes, most likely by Apple engineers, because Apple engineers are, a lot, they fly down to China, but a lot of times they're in Cupertino or Austin monitoring what Foxconn factories are doing. So this is an obscure hardware feature that was only used in the manufacturing process itself, never published, and it doesn't even look like it was recently used, and yet they still found it. They still found a way to attack it. This is really a marvel of an attack, and probably the reason I'm including this is because I think ultimately you have to understand how everything about your design could be attacked. Ability to write into any unsecured storage area or memory space can be used to load malicious code. And this is how you should think about possible attack vectors, right? When you think about, a lot of times when we look at vulnerabilities and exploits, we can talk about, and this is where you can lull yourself into a false sense of security. You can look at an attack and say, well, this one looks really hard to execute. It requires local access, elevated privileges, and a device that normally wouldn't be accessible unless you had physical access to it. So look, no remote exploitability, no way to just, to get physical access to a device. You would be surprised. You can still attack these devices, and I'll show you exactly how those attacks are executed. Brenden, anything to add at this point? Any takeaways from these slides?
As we'll talk about later too, I mean, this is a good example of, at early stages in development, it's very easy to leave all of these great hooks into both your hardware and your firmware to make it more easy to debug. There is a critical step there of legacy code being left in or not enforcing your validation and test stages if you're running a CI/CD process to enforce that those things are turned off or removed or compiled out as opposed to getting left in. So this is a thing we'll talk about later as well.
This is another example, and this was for me personally was pivotal point. It was disclosed in 2015, and by the way, we did include links in here to these reports. look, there's a ton of information published about how attacks work, how they're executed. In some cases, kind of the genealogy of them, who is actually executing them. In this case, these are reports, and why would somebody publish these? You can think about the cybersecurity world again. If it's not commercially minded attackers, a lot of times it's nation states attacking each other. For years, we had this really strange situation where Kaspersky's Labs, which is a really popular antivirus maker based in Russia, for some time we really decided that Russia is nothing to be worried about, and Russian software, antivirus software loaded on a bunch of government machines wasn't a big deal. I think eventually we came to our senses. So Kaspersky was kind of unceremoniously kicked out of most government installations. I'm still kind of surprised that they're still being used in a whole lot of commercial situations. So there's a lot of companies using Kaspersky out there. Look, there's a lot of links between Kaspersky and Russian government. The people that started the company are ex-GRU. It's the motherlode of bad ideas. You really don't let foreign adversaries write cybersecurity software for you. But for that reason, what the NSA and Kaspersky love to do is publish really amazing white papers on how they attack each other. Because once you expose somebody's attack methods, they are, for all intents and purposes, burned. So a lot of times we learn some of the most amazing things because Kaspersky Labs or Russian intelligence revealed them to us. And this is one of those cases in 2015. This is the one where I really, we at the time advised a lot of clients on how to secure their environments. Look, and the typical guidance for everybody is most of your attacks live in user space. Sometimes they're in kernel space. But in either of those scenarios, yes, you may get compromised. A lot of times these were self-propagating threats. So we're talking about, it's not like these were surgical attacks. Back in those days, 2000 all the way to probably 2018 or so, still just a lot of worms roaming around and just massive numbers of machines on the internet getting compromised, some trivial, some really important. But the typical thing you tell anybody is, look, reinstall the operating system, do a hard reset. Sometimes, look, scrub down your disk, you'll be fine, right? In this case, it became obvious that no, you're not fine. And in fact, when Kaspersky talks about the equation group, they're really talking about the NSA. That is who solves the equations out there. But in this case, the malware itself was loaded on hard drive firmware. It's obvious that it's a nation state doing this because they didn't take any chances, and they didn't just say let's cover Seagate in Western Digital because we know the targets we're going after are going to be using those hard drives. They covered everybody, right? They covered every hard drive vendor out there. The MCU on the motherboard wasn't used at all, right? So this requires no awareness in a user space, no awareness in the kernel level. Even the motherboard itself doesn't need to be aware of this attack. Ultimately, when this firmware gets compromised, it is resident and hidden in invisible storage sectors, survives a reformat, survives pretty much any sort of eradication scenario we can think of. So think about a scenario where a worm spreads broadly all over the internet. Everybody tries to clean it off. They use typical countermeasures, reformat devices. But ultimately, it still persists. It is still, the malicious code is still on the drives. And as long as you're literally not throwing away these computers entirely, your attack will continue, right? You will continue to advance forward towards your attack objectives. This is where I kind of threw my hands up and decided, there's only certain things we can do. We can never eliminate attacks like this. Now, thankfully, this happens once in a blue moon. Now, you have to ask yourself, why would somebody go through all that trouble to compromise all those hard drives? These things are not directly related, but we certainly know that the most complex and really the attack with most payoff, right? There's a lot of attacks out there where, billions of dollars get stolen. especially after Bitcoin came out, it just became, for people that are out there for the money, there's no shortage of ways to make money, right? Spam is still a reliable source of income for low intelligence attackers out there, right? And for people that are a little more creative, stealing cyber currency is the low hanging fruit. But if you're talking about attacks that actually matter, right, and this is where industrial systems get compromised. This happened multiple times in multiple mediums, but no example is as impactful, I think, as the Stuxnet worm ultimately disrupting the Iranian nuclear plant. The end objective for this attack was to slow down the Iranian weapons development program, and they ultimately got the centrifuges to miscalibrate it enough to where they ultimately destroyed themselves, right? The rotation was disrupted just enough to where essentially the useful life of these centrifuges was dramatically lower. And I think, I don't remember how long it took, but it wasn't immediate, but it clearly just wiped out all the centrifuges at this refining facility. Now, how do you get there? And this is where the puzzle starts to get put together. In fact, this attack must have taken many years to execute. And when in the prior example that we gave you, by 2015, when Kaspersky disclosed their awareness of these hard drives being compromised, it was actually clear that when they were compromised was more around 2008 timeframe. And by then, it was, I'm sure the NSA guys were sad that their work had been exposed, but at that point, that program had already been concluded. So there wasn't major harm done to that disclosure. Now, why was it necessary? Because it was a multi-year program to penetrate pretty much everything in the Iranian nuclear development program supply chain. And without knowing how you're going to get into these environments, you have to compromise everything, right? And so they started early. We're aware of first of all, multiple electronics component makers being compromised early on. Those components ultimately made it into some of the PLCs and some of the devices used to control the actual industrial environment at a lot of places, but especially this Iranian nuclear plant that they were going after. Again, multiple points of entry, multiple seemingly unrelated manufacturers, right? In this case, it was everything from centrifuge makers to component makers. And they were just putting together a picture where they had a lot of access to everything that's used in this nuclear plant. Because ultimately, the reason why it's so difficult to attack these environments is because they make them inaccessible, right? Ultimately, when you're building an industrial control system, it is supposed to be air-gapped, and it is, right? So these are devices not connected to the internet. They're not being used by people that can bring malicious code with them. So I think the Iranians knew what they were doing. I think they built their systems right using best-in-class security guidance. I don't believe that they did something stupid, and I've seen that before. I've seen oil rigs where an air-gapped network was, for whatever reason, bridged to the internet link, and it just made it easier for them to upgrade their Windows systems. You'd be surprised what they still run on oil rigs. I don't think Iranians made any of those mistakes. I think the attack was good enough to bypass every possible control they put in place. So the way this thing spread was they let out a worm, and that was Stuxnet worm. Actually infected a lot of people, right? Notice in the prior slide, it talks about global epidemic. This really did spread broadly. They tried to control it regionally. So if you actually look at a map of Stuxnet, it was smart enough to say, I'm in Western Europe, I don't need to go further. I'm in North America, I don't need to go further. But if it was anywhere in Middle East, if it was anywhere in Central Asia, it would continue going forward, right? Rough level of just propagation control. They directionally landed it in the right place. If you were to ask those hard drives that we talked about earlier, how do they get firmware onto those hard drives? The entry point was, believe it or not, a research conference, right? A researcher came to that conference, went to the conference, went home, in the mail received a CD-ROM full of pictures and papers, right? And loaded that CD-ROM locally, and that is how it ended up in some of the intermediary layers where scientists at these plants work in their environment. Still not the inner ring where there's a SCADA network that is actually air gapped, but got close enough. And ultimately, that's how it spread from one step to another using stepping stones. And this is probably the ultimate example that I want to land to help you understand that you may think your IoT device doesn't matter, but it does. It may not be the ultimate end step in the attack kill chain, but it may be a way to just bridge the gap between two networks that should never be talking to each other, right? And ultimately, they reached their objective by 2010. They were in the centrifuges and successfully were able to launch to execute their attack. But again, a lot of people got infected with Stuxnet. That wasn't the objective of the Stuxnet worm. The objective was to get into every possible crevice of every environment. And look, they went after everything, right? In places where they couldn't get the worm to reach them, as I mentioned, they used researchers, right? It's kind of interesting, that research conference, they actually know which one it is. It happened to be in Houston, which is where Brenden and I live. So I think that's ultra cool in general. So the thought of NSA operatives at a hotel in Houston delivering CD-ROMs to infect people in Iran sounds like a really just a lot of effort. And again, there's only a few people in the world that would undertake something like that. But ultimately, why was Stuxnet so successful? Look, it's two macro reasons. One is that if the two best cybersecurity agencies in the world, and that happens to be US and Israel, if they want you, they will get you, right? Russia is really good. China is really good. To be frank, China was successful in stealing most of the industrial secrets from US, not because they're so phenomenally sophisticated. I think it's because we're so phenomenally bad at cybersecurity. In fact, we are way too lax with where we allow our data to live. We think that a compromised environment is a nuisance, and in fact, they're stealing critical data in a lot of ways. But ultimately, the really sophisticated stuff is done by US and Israel. So if US and Israel want to come after you, it might take them a long time, but they will figure it out. The bigger problem is that Iran does not control their supply chain. So, and you saw it on previous slide, I'll back up a couple. You'll notice that they use as much of their own infrastructure as they can. Sometimes they had a local centrifuge developer, right? And I don't think they used all 100% of centrifuges from this company, but this was an Iranian business, I believe, right? But at the end of the day, they just don't have enough to build everything they need in a nuclear refinement facility from equipment that comes from Iran. They don't control their own supply chain. So the biggest variables in that attack kill chain were Siemens PLCs and Vacon variable frequency drives. I'm not, to be honest, I'm not an expert in how centrifuges work, but my understanding is that those variable frequency drives are what drives even the Iranian-made centrifuges. So look, between the US and Israel, they had enough intelligence about which specific versions of Siemens and Vacon equipment were out there. So that is how they were able to limit the actual blast radius to specific environments that they wanted to attack. They were very certain that if they were going to go destroy the centrifuges, they're going to do them in Iran and not necessarily in other places that use this equipment, right? Look, controlling or failing to control your supply chain is the ultimate flaw, right? As long as that is wide open and unsecure, in a lot of ways, you're basically inviting attacks in. And this will be the last thing that I want to touch on. and to be honest, I really didn't understand the gravity of this when I was in the cybersecurity world. Only when I joined MacroFab did I understand just how distributed the supply chain is, and the fact that we take our electronics design files, really some of the more sensitive stuff, routinely send them to China. When I talk to largest companies out there, they typically take their supply chain seriously, if they take it seriously, when it comes to production. A lot of times when it comes to engineers, they don't care. They don't think of that as a way to leak information, but in fact it is critical that this information shouldn't be spread all over the world. Even as much as not sending this to China is sending your prototypes to friendlier countries will keep you more secure, right? It's obvious that when they land in China, they will be hoovered up by the second largest, maybe not the most sophisticated, but second largest intelligence and cybersecurity apparatus outside of US, right? In general, I find that cybersecurity teams in companies have no idea what electronics engineers do. They don't talk to them. They don't understand how electronics products are put together. This happens I think it happens the right way in very, very few companies. But in most cases, I would say there is a state of planned ignorance where the cybersecurity team doesn't really want to go talk to the engineers and vice versa, and they kind of very carefully avoid each other. And ultimately, the final thing I want to mention is, and this is unproven in my experience. I don't know. I didn't put this as a slide in the deck. We have plenty of slides, but a couple of years ago there was a very loud article in Bloomberg about super micro motherboards getting compromised. There was a lot of theory. There wasn't, nothing was ever conclusively proven. There was no evidence given, but the supposition was that super micro motherboards were compromised at a manufacturing stage. Some of them were sent specifically to Apple, Amazon, and a handful of other cloud providers. Again, not proven, but in my experience, rumors like that eventually do get substantiated. So I think our control over the actual manufacturing step in a supply chain is largely non-existent. Again, if the cybersecurity teams don't talk to the design engineers, they definitely don't go to factories and understand how that data is controlled, where the components come from, where they're purchased from. If somebody wanted to insert malicious components into a factory somewhere out there, it's not that difficult, to be honest. So that is certainly concerning. I think there's a lot of room for improvement along the way. I'll turn things over to Brenden at this point. He is the electronics design expert, so we'll get into specifics on that front. But I'm certainly going to be here, happy to answer any questions and continue the discussion.
Yeah, thank you, Misha. So looking at ways we can actually mitigate some of those attack vectors that we're talking about, as we mentioned at the beginning, one of the big ones is, and this permeates not just in firmware but also in the hardware as well. A lot of your debug points, a lot of things that make your design easier to work with or to test with, are also easy things to allow attackers to learn more about your system. So specifically things like leaving all of your test points exposed and well named. It can help to try and hide any of the copper that's on the top of your board underneath in internal layers so that it's harder to probe while it's under operation. So you can do things like routing your signals only on internal layers, using blind and buried vias. Going back slightly too, when we talk about the quoting phase, all the time we will receive quotes from procurement or engineering that will have your schematics in it. It will have the firmware files they intend to put into the final microcontrollers, and it will have just detailed instructions on parts of the design that are not necessary for quoting and also are only really necessary when you finally select your manufacturing partner to go to production with. And so trying to reduce the amount of data that you're spreading around outside of the quoting stage can be key. Furthermore, kind of on the securing your ICs and a little bit of security through obscurity, You have probably seen this before when you've opened up products. If you like to look and figure out how things work, you'll see blacked out chips, fully encapsulating critical ICs, people using complex package choices just to make it more difficult to probe, right? If part of this step is to learn more about your product and try and understand like what signals are being carried on what lines, making it difficult to probe while it's still operating can be a huge help there. When we talk about firmware security measures, which is a big part of this, as we mentioned before, removing test and debug code hooks. I personally like to enforce this as part of your CI/CD process for firmware. You actually want to like make sure that that code is not being compiled in. You want to make sure that you aren't leaving those hooks, and the fact that when you go into your unit test, your integration test, that you are actually testing that those are removed. It feels like low-hanging fruit to say, don't leave your UART headers labeled on the edge of the board and operating, but that happens all the time. Like you'll look at news of people like you go into production, they left the shell open on their device. So that's like kind of low-hanging fruit we should be looking at, but it's important to remember, and the best way to prevent accidental mistakes there is to enforce that through testing. Using secure data storage, again, similarly, if you're offloading your storage outside of your main microcontroller to another device, it's a lot easier to intercept that data in flight, or to have other attack vectors that are easier to get at, that don't require as expensive as equipment or more complicated methods to attack. You don't want to. You'll see again. This happened with a recent like Bitcoin hardware wallet hack where they were able to get the secret keys while they were being moved at startup during runtime. And so trying to reduce the amount that you're actually accessing and moving the data around during runtime can also help prevent data potentially moving into unsecured sectors, things like that. When you're selecting hardware components, using vendor-provided trusted modules or secure storage is big. Like we talked about before, you can't prevent, necessarily nation states targeting your device, but in terms of companies that have the resources to try and prevent those attacks, some of the large chip manufacturers who are providing the tools, those are things you should be taking advantage of. You want to, again, low-hanging fruit, sign and encrypt your firmware packages. You want to prevent malicious code from running on your devices. And another place where common mistakes happen is trying to roll your own cryptographic methods. Like ideally, we want to be using standard cryptography methods. It's easy to make mistakes when you are trying to develop your own methods. When we talk about manufacturing for security, this gets very, very broad, but a good starting point is develop a plan for how you are going to share your secrets and your firmware at the time of manufacture, right? There are a bunch of ways to approach this, all with their pros and cons. You can do things like pre-flashing your devices before they get to your manufacturer, where you're actually controlling it, or you're developing custom software solutions that are running at your manufacturing facility to generate these keys and to put them on each device, right? Again, the base assumption here is like every device is using different keys. Attacking one doesn't necessarily compromise the secrets of others, but a good start at this, because it can be very dependent on what your device is to develop a strong plan early on in your product development lifecycle of how you're going to approach this, and make sure you're designing this as part of your overall kind of product spec. You want to, again, minimize data exposure during quoting. You don't need to send your firmware out during quoting. You don't need to send out your schematics during quoting. These are the types of things that you want to hold close until you actually have selected a partner and are ready to go through those stages. When we talk about some of the other approaches for physically securing your PCBs, one of the things that can make it really difficult to attack a design is fully encapsulate your PCBA with epoxy or potting. It makes it really difficult to probe. The only way you can really look at it without disturbing it is using things like X-ray and other methods. You want to use tamper-resistant enclosures to prevent, again, access to the bare board. Unique and custom fasteners, again, just slowing things down, and overmolding and ultrasonic welding can also fit in that realm. When we talk about tamper detection, now that, let's say, they've cracked open your enclosure, a great next step, especially as battery powered or something similar, is as soon as you detect that intrusion has happened, you want to put in place some things that are not just like fuses that get blown. Those can be repaired. You want to do things like full self-erasure if possible, zeroing out critical data immediately, just bricking your device as soon as that happens so that it's not recoverable. You want to shut down and permanently disable, because if they can repair the detection method and get you back up into a runtime environment, it's easier to attack as it's running. When we talk about security testing, this is similar to what we talked about before, where you want to have a plan for it. It's easier to prevent common mistakes by actually enforcing these checks during your development process. So when you're doing hardware in the loop testing, make sure that all of your low-hanging fruit is taken care of, like your shells are turned off, you can't read any debug output, but any of the other security features that you have as part of your spec should be tested at this time. Mandating removal of firmware and debug test hooks and enforcing this through regular regression testing. You want to stay up to date, especially if you're using something like a trusted module from a vendor. Like, pay attention to their security updates, the errata that they post, the type of attack vectors that they know about, and the silicon that you may have already deployed. You want to keep up to date with that. You want to update your firmware regularly to try and mitigate those attacks, and stay in regular collaboration with security experts. Another good step is potentially looking for manufacturing partners who use ISO compliance for quality. As we talked before, like, this can be part of a design issue, things that you need to actually continuously monitor. ITAR, which is a regulation for data integrity, especially when it comes to defense and critical technologies, not sharing data unnecessarily, and strong quality and security assurances from the manufacturer that you select. As Misha also mentioned, training is a big part of this. There are a lot of, especially on the hardware side, it's less common to have this thought process about designing for security, and it's important to make sure these trainings and awareness events are directed to all of the engineers at your company, to make sure that at every step of the way, whether it's during supply chain and procurement, like who you're selecting as your vendors, as well as at the design stage for both hardware and firmware, these are things that your engineers have at the top of their mind. Leaving time for questions.
All right. Thank you, Misha and Brenden, for that great presentation. It was really insightful and definitely gives us a lot to think about in the realm of security. I want to kick things off with the kind of leading off the thing you just mentioned about training for staff across an organization. How do you guys do that internally, training your hardware engineering, your procurement teams? What do you guys kind of do? Because like you said, there's not a lot out there necessarily that's set at training that type of individual.
Yeah, on our side, speaking from the manufacturing standpoint, a lot of our training is devoted to how to handle the data that we are entrusted with, right? From the NPI stage, right, where we're developing work instructions, making sure that we're not oversharing details of the internal workings of a design, how we treat it in our systems. Misha can talk also about our ITAR compliance, things like that. But a lot of our training has to do with making sure that we are treating data properly.
Yeah, look at some of it we just can't help ourselves. We come from a cybersecurity industry, so the software development team has a number of ex security developers on it. So for that reason, we built a resilient platform. So really, what we focus on going forward is improving the process. Sourcing process is probably most important, and a lot of. And by the way, this isn't strictly related to cybersecurity. It's also related to just making sure that the devices that we help our customers build are built properly and perform as expected. That requires sourcing components and knowing whether they're authentic. And a lot of times when we have sourced components and our team internally found out, and this usually happens. It happened more during the supply chain crisis when usually we buy all of our components from authorized resellers. You know the chain of custody for those components fairly intimately. You can call somebody like Avnet or TTI and understand where they source them. They have their own very good security programs. But during the supply chain crisis, a lot of times you turn to secondary suppliers. Customers approve it because they need to get components. That is where our second tier protection kicks in. We make sure to scrutinize those components, have found a number of counterfeit parts. In some cases, go send them out for secondary testing. And look, a lot of times those counterfeits are happening for purely commercial reasons, but attackers will take the exact same route as well, right? If you had a way to land ICs that are compromised, you would want to insert them at a manufacturer like MacroFab, right? So we have a lot of processes in place to make sure that that never happens.
Excellent. That makes a lot of sense. Thank you. All right. Our first question here from the audience is asking about what about JTAG interface protection?
Yeah. So especially if you're using kind of the standard JTAG interface, where you might see where you're using the test points to program your device. A lot of this comes down to effectively trying to make a one-time programming setup where, as part of your firmware, looks for certain conditions, like whether it's at the manufacturer or not. If those are present, then you can go ahead and do your programming and interface on your JTAG part. But as soon as they're not present, similar to tamper detection, you disable the port, you ignore any data on those lines. One of the things you can also do, if you want to go an extra step, you'll see this recommendation in other hardware security sort of bulletins as well, is you can turn all of those pins, if possible, to inputs and start looking for strange activity on them, so that if someone is trying to basically scan all the unused pins on your board or trying to get at your JTAG interface, you can immediately disable your device as soon as you are seeing sort of errant behavior or kind of unexpected voltages on those lines. You can try and defend against that.
Oh, okay. That makes a lot of sense, especially to be more proactive and not just passively ignoring the thing, but trying to look for those possible threats.
You'll see a lot of this happens with, like I mentioned before, there was an attack on like a hardware Bitcoin wallet. One of the things they were doing is basically trying to glitch the chip by making it operate outside of its intended power supply standards. And so again, trying to detect that. So that as soon as you start seeing things that, the power supply in your design, the range it should be operating in, as soon as it's outside of that range, it is probably a good sign that you may want to try and secure your data.
Okay. This is a fun question. Firstly, thank you for this excellent webinar, but what is a recommended entry career path for someone interested in hardware security?
Yeah, great question. I would start with getting a good background in hardware design is obviously key for this. Starting out, I also find that if you want to try and get more of a broad sense of different industries to figure out kind of where in the hardware security path you want to end up. The personal path I took is I started at kind of like engineering shops where, we would work on a wide range of industries to get more exposure to that. And then from there, start targeting the areas that you're interested in providing security for once you get experience kind of across a range of industries.
Very good. Thank you. This question is, what do you find are the most common mistakes that companies make in their PCBA security?
Yeah, we touched on a couple of those. But again, the main ones are sort of the accidental mistakes that happen when you don't enforce the kind of procedures you put out in an automated way. It's very easy for people to make mistakes at like final hardware QA stages or with non-automated tests to forget to check, to turn off the debug output, or, it's up to an engineer at compile time to actually like make sure that they add the flag that says like turn off debug or turn on optimization, which is another good way to add security through obscurity. If you're manually doing those things, it's easy to make those mistakes. So a lot of this is once you make a decision on a security approach that you want to take, try and enforce that through automation, and then double check yourself through testing.
Look, I'll add to that. I think vendor selection will probably be, and I know that doesn't sound glamorous, but that's very much at the top of my list. And that's because we deal with just a lot of scenarios where vendors are considered. In my prior life in software, we would constantly get bombarded by, cybersecurity teams interrogating us about how our cybersecurity practices work, who we are, checking our backgrounds. That almost never happens in the electronics field for whatever reason. I can count on my hand the number of times we've gotten cybersecurity questions. They're usually perfunctory, such as, do you have a policy? Yes, we have a policy. We wrote one. But ultimately, we just don't see a whole lot of attention paid to who the vendors are. And that tells me that somehow other considerations have become more prominent. And I just disagree with that approach. I think saving, 10% on a PCB design from a vendor you've never heard of probably isn't worth it. So I think vendor selection would be at the very top of my list. There's and I think the supply chain process in general, where your design may be completed, hand it over to your supply chain team, and they will happily spray it all over the internet to try to get a low price, doesn't sound like a good idea to me at all, right?
Yeah, and those insights were fantastic. So thank you for those answers. It kind of really lead into, I think, this next question of where do you guys see the field of PCB security heading in the next 5 years to address the problems you're just talking about?
Yeah, from the design side, I think specifically as we talk about the increasing prevalence of IoT, almost all products tend to be connected now. I think this is going to be more prevalent when it comes to threat mitigation, not just for the IoT product itself, but for the areas that they're built in or the products they're supposed to work with, right? The standards that they are supposed to be a part of, whether it's like Matter or direct Wi-Fi or whatever it is. This is going to be a more prevalent question that they'll be asking, like, hey, this is a connected product. How are you defending against this? At least the initial stages of trying to prevent attacks at the lowest level, not just at whatever RTOS you've selected or whatever your backend is.
There is in a cybersecurity circles, it's a pretty emotional field, believe it or not. But there's this never-ending debate about whether anything that on a defensive side that we do is ever actually working. And there's a lot of doom and gloom, and just in terms of, look, we keep on trying to build a perfect system and they keep getting cracked. I think that both of those things are fundamentally wrong. I don't think you can build a perfectly secure system. That's a fallacy. You can reduce your attack surface and you can make it harder to compromise you. I don't think a perfectly secure system exists. More important, I disagree with the notion that nothing ever improves, nothing ever changes. In fact, everything is always changing because the defenders are getting better and better, right? Look, the very fact that we even cryptographically sign firmware these days is already a small miracle. That used to not be a thing at all. We have gotten much, much better at every aspect of security. Now, I will tell you that because it's easier, software gets overwhelmingly more attention in terms of security audits, controls, and in some cases, just smart people thinking about it than electronics. For that reason, it is harder to compromise software these days. There are a lot of people out there that specialize in software security, much fewer in the electronics world. So the very simple fact that we're just not that good at this yet when it comes to hardware and electronics, it gives attackers ultimately a bigger attack surface. So I would expect more attacks and more people spending time securing these devices, just the way Apple does. Apple, I think, does a phenomenal job of securing their designs. The rest of the world has a long way to catch up, right? And I think no industry is worse at this than industrial control systems, right? They're still using Modbus and, we're talking about protocols that were designed 40, 50 years ago and haven't been changed. because change causes things to stop working.
Yeah, and I think those concerns, looking at the polls that we ran during this seminar, and the concern, and the overwhelming majority of people expressed that they are at least moderately, if not very or extremely concerned about the reliability and security of their supply chain for PCBs. And I think as electronics extend into those industrial networks, and like you said, use some of these older protocols, there's a real threat. As you guys looked at those polls, any interesting insights from the audience that surprised you maybe in the answers?
I have not looked at them.
Oh, okay.
Yeah, I think that when we look at the results for how concerned is your organization about the reliability and security of your PCB component supply chain, I like the very nice even distribution there. I think this is one of those things that it can depend a lot on the type of design you have as well, right? Mm-hmm. If you're doing a non-connected design, or potentially you're doing a totally analog product, this probably isn't that much of a concern to you, right? There's maybe like nothing there that you need to be concerned about, but definitely organizations and products that are running firmware or connecting to things, or supposed to work with peripherals, those are the things I think where people definitely get more concerned about it.
I see there's a question here about whether a victim has counterattacked the abuser. Always a vibrant debate about that, and it's a lot of fun. To be honest, there's not a lot of payoff. What you have as a defender is a lot more valuable than what they have as an attacker. You can't really hurt them all that much. They're using, look, in some cases, they're using somebody else's systems to attack you. So you probably be attacking somebody who is uninvolved and maybe roped into the whole attack kill chain simply as a stepping stone. So there's a really good chance you might counterattack somebody who will sue you because it's a real company. For a lot of reasons, this never breaks out beyond the fantasy world. There have been some companies that got venture funded to do just that, but it really doesn't. It's not a major thing. Defense is really the ultimate objective, and there's just not enough pain we can inflict on the attackers to make this worthwhile.
All right. Well, we're just about out of time here. Any last takeaways you guys want to share with our audience before we wrap stuff up?
I'll just briefly answer the last question that's still available too, as
okay,
kind
sure.
of a takeaway. When we talk about this, especially at the design stage, when we're talking about PCBs, one of the main, the first step you should take is not just at the component selection and sourcing, it's really at your architecture phase, right? When we're talking about especially combo products with firmware and hardware, what kind of data are you going to be storing? Where are you going to store it? How are you going to update it? That initial phase of the architecture of your product is critical to determining everything that comes after that, right? If you're going to store some data off board in something else, maybe that's fine if it's not critical data. If you need to store critical data, it needs to be on microcontroller, potentially in a secure module, things like that. So I would definitely start at the architecture phase.
Excellent.
There was a quick question there about red and blue teams and hardware security. Those actually do exist, and they exist in some of the better funded organizations out there. It is a good idea to do, right? And I would use an outside party to do this. You don't want somebody with inside knowledge to do to be the red team. But by the way, the idea is to have somebody try to compromise your device and see what your actual you need to find somebody that really knows what they're doing. But there are consultancies out there that are really good at this. It's probably cheaper than you think. I think it's worth doing. My final closing statement is, the electronics world is a lot less community oriented, I find, than software and cloud, and the AI world is very chatty. We certainly can build more water coolers around which to have a conversation. So I would encourage you to listen to our Circuit Break podcast. Those run weekly, and we touch on a lot of these topics. And more important, we have a community as an offshoot of that, so you can come in and discuss that in our Discord environment. So I think there's just not enough places for electronics designers to actually have these discussions. I would encourage you guys to reach out and actually get to know each other.
That's beautiful. Yeah. So Misha and Brenden, thank you for your time today. A great presentation and great discussion in the Q&A. And thanks to our audience for your participation. Had some really strong questions today. Appreciate that. Everyone, in just a moment, you'll be redirected to MacroFab's partner content page on All About Circuits, where you will be able to view this session on demand and check out some other great MacroFab resources. So thanks everyone for your time. We look forward to seeing you at another live session again soon.